Hi, my name is Amir. Now I will presenting about background of VCM production. So basically, what is VCM? VCM stands for vinyl chloride monomer, which is the monomer that we use to produce PVC. So it's like a monomer, like raw ingredient to make plastic, like any plastic, like this plastics and also this plastics to create a plastic. So monomer is used to production of PVC, which is polyvinyl chloride and plastics, and mostly most important ingredient among now current industry. So the production of VCM take about two reaction, which is reaction between C2H4 and chlorine gas. And we can the reaction of C2H4 and chlorine gas, we can get ADC, which is ethyl dichloride. So and then the ethyl dichloride need to decompose to two other component, which is the VCM, vinyl chloride monomer, and the other one is hydrochloric acid. So the overall reaction is, as we can see in the slide, which is C2H4 plus Cl2, we can get VCM and also hydrochloric acid. So in these studies, we only focus on distillation column C202. So it's actually is function of distillation column is to separate the VCM and also the EDC. So VCM in the top because the lower boiling point, and the EDC at the bottom because it's higher boiling point. So next.
Okay, before we move on to the incident outcome, I would like to describe the cases of scenario when the incident occurred. The first scene is a plant have 20 operators working in a process area on day and night time. Next scene, which is scene 2, is an administrative office, is located about 500 meter from the process area with a population of 40 staff on daytime. And the last scene, which is scene 3, is a residential area, is located about 1 kilometer from the plant with a population of 500 people. Now, we move on to the first incident outcome that might occur, which is explosion of distillation column C202 for our case. Explosion occur is due to overpressure of distillation column. There are two types of explosion, which is vapor cloud explosion VCE and boiling liquid expanding vapor explosion VLEVE. For our worst case scenario of scene 1, the distance from the ground zero point is 10 meter from distillation column to C202. The scale distance ZE is 0.5229 meter per cube root kilogram with the scale overpressure of 7,409,192 Newton per meter square. After calculating the probability and percentage of death and damage, the percentage show that the explosion caused death of 20 people from lung hemorrhage and eardrum rupture, and also 100% damage of structure and glass breakage. For scene 2 we assume its worst case scenario. The distance from the ground zero point is 500 meter from distillation column C202. The calculated scale distance ZE is 26.096 meter per cube root kilogram with the scale overpressure of 6,606.9 Newton per meter square. After calculating the probability and percentage of death and damage, the percentage show that the explosion caused death of 0 people from lung hemorrhage and eardrum rupture, and no damage to structure is done. However, the explosion caused 92% of glass breakage. Now, we move on to scene 3, and the worst case scenario, the distance from ground zero point is 1000 meter from distillation column C202. The scale distance is calculated to be 52.19 meter per cube root kilogram with the scale overpressure of 3,235.325 Newton per meter square. After calculating the probability and percentage of death and damage, the percentage show that the explosion caused death of 0 people from lung hemorrhage and eardrum rupture. No damage to the structure is done, however, the explosion caused 29% of glass breakage, lower than the case 2 scenario. So what I can conclude is the further the distance from the distance of ground 0 point from the explosion, the lower the rate of damage to property and death of people.
Let us move on to the next incident outcome, which is the fire. Fire is the most common accident that can occur in chemical industry, whereas fire is the rapid exothermic oxidation of ignited fuel. Whereas for the fire or combustion to take place, there should be three main elements consisting of heat, fuel and oxygen. Neither of these present or combustion will not occur. There are three main incident outcomes that we have tabulated, which is the first one is a plant having 20 operators working in a process area day and night time. Scene 2 is about administrative office, which is located about 500 meters from the process area with a population of 40 staff on daytime. Whereas the scene 3 is about residential area located about 1 kilometer from the plant with a population of 500 people. For the first scenario, the worst case scenario, the distance from the ground 0 point is at 10 meter from the C202 VCM distillation plant. The incident thermal radiation Q obtained is 448.167 watt per meter square. After calculating the probability analysis and the percentage of fatality, the percentage shows that the fire caused 1 out of 20 operators working near C202 VCM distillation plant has been dead. Therefore, immediate action should be taken place, where the operator should be wearing personal protective equipment in order to reduce the damage from the fire. Other than that, alarm system should be provided in order to sound when any fire or heat can be sensed, thus making the operators to react to the sound and immediately run to the safe zone. The next worst case scenario 2, which is the incident thermal radiation value obtained is 35.972 watt per meter square. The probability analysis for the percentage of damage or death is 0%. This shows that no workers has died and the fire has not affected the workers working on the administrative office due to distance between the worker and the flash fire occurring is far, thus no fatality happened to the workers. Thirdly, the worst scenario case is scenario 3. The incident thermal radiation Q obtained is 9.588 watt per meter square. The probability analysis for causative variable from fire burn deaths from flash fire, the percentage of death or fatality is 0%, proves that no residents has been dead. This shows that due to distance between the flash fire and the residential area being farthest, no fatality nor death has occurred. The purpose of constructing flammability diagram is to give insights on how a gas or mixture of two gases will behave and catch fire with dilution of other gas on air. Therefore, it is important to construct flammability diagram for VCM production due to VCM being carcinogenic to human health, which can cause cancer. From the flammability diagram, the LFL obtained is 4%, whereas the upper flame limit, which is UFL, obtained is 22%. The Z value obtained from the stoichiometric equation is 5. Thus, the obtained value of stoichiometric line is at 83.33%. Thank you.
Next my part is the probability analysis for toxic release. As we can see, there are three parts in this studies, which is about 20 workers exposure to daytime and nighttime. So the concentration that we get in ppm, which is 1087 for 67320.6 ppm, which is in the probability analysis, the probability is 21.027 and the percentage of death is 72.9%. 0.34. So 15 no. So 15 operators are dead due to the excess exposure of the EDC regarding the leakage exposed over 12 hours. So the next scene is 40 workers exposed for 480 minutes. So we can get the concentration, which is 1165. So we can see here 116562.44 ppm. So the percentage is 153.52, which is 100% death. So all the 40 workers are dead in this scenario. We assume it is overcast because it's easy for the calculation, and the wind speed, the average wind speed is 5 meter per second, like typical wind speed at this industrial area. Lastly, for the scene 3 is a probit for the residential nearby the plant. So there are 500 people that are exposed for about 24 hours. So the concentration that we get at 1 kilometer away from the plant is 2.64 ppm. So the probit is negative 1.70. So the percentage of death is 0%. So there's no death in this scenario. So that's all from me. Thank you.
Hi, very good morning. Okay, so for today, I'm doing like the part of hazard identification. Hazard identification is the first ever step we want to notice, or we want to know the risk that can further to and become the consequences of in every process plant. So for our project, we got distillation column. Our project, there have like 4 different parameters that we going to identify the hazard that can be occurred. The first one is pH value, second is flow, temperature, and the last one is the pressure in the distillation column. So based on the parameters that we have, we will identify if there is any bad consequences that are going to be happen or not. So that's all for today. Thank you.